Hi everybody, and welcome to this episode. I'm in Wenatchee today, and I'm in the backyard. This is Plan B. I had plans to join Ralph Haugerud, longtime USGS geologist, up in the North Cascades this week, and we may still get up there, Ralph and I, but this amazing home that Ralph has now overlooking Wenatchee, you can see the smoke. We can't see the Columbia down there in the distance. So we're to Plan B, which is kind of talking about the North Cascades out here at Ralph's patio. Thanks for joining us. Let's flip you around and start visiting with Ralph. This is a kind of a part two, I suppose. Mm-hmm. We visited a couple of years ago, late summer, and we got your backstory, University of Washington, Western Washington, how much you'd been working in the North Cascades, and that abruptly kind of stopped in the mid-90s. Why haven't you been as active in the North Cascades as you were before? What happened in the mid-90s?
In the mid-90s, my job changed. The Geologic Division of the USGS went through a reorganization in response to a long-term decline in minerals prices. And I moved from doing framework geology, regional geologic mapping, to doing geology in populated areas focused on geologic hazards, primarily earthquake hazards.
Okay.
And so I went from the North Cascades to the Puget Lowland. And I learned about LIDAR and about glaciers, and I've been thoroughly entertained ever since.
Well, yes, and that work it stands alone, of course, as well. But at the time, was it painful, that transition? Did you fight it somehow? Like, hey, man, I'm invested. I got 2+ decades with all this North Cascades work.
Yes and no. In part, it was very challenging to leave the high country. And if we make it up to Slate Peak later in the week, you'll discover you'll have a very hard time getting me back in the car. That's home. I belong there. The other thing is that coincided with my knee going bad. And it was clear to me, I was thinking about doing the bedrock geology around Lake Chelan as sort of the next task. And I had severe doubts about my ability to do that. It's a brutal landscape if you think about traversing from lake level at 15,000 feet, 1,500 feet, up to the ridge crests of 7,000 and no water along the way.
Right.
And no helicopter support because it's all dedicated wilderness. How do you do that?
Yeah.
And so it was okay.
You know, as I approach you to talk about the North Cascades, I guess you could say, I haven't been in the North Cascades since 1994 or whatever. Go talk to somebody else. How much have you been involved? Like these field guides that I keep using, you're editing those things.
Well, this map's got a publication date of 2009, and it's been a couple years in publication after we created it. But Roland and I were very actively thinking about North Cascades geology throughout the first decade of this century.
Okay.
And I have not worked on the old rocks, the North Cascades, or thought about them much for, well, almost 15 years. But I still think very much about the younger geology, and am actively working, in this map area in the North Cascades, but on the Eocene and younger story.
Well, thank you for getting this out and laying it out for us. You want to share what you told me before we started about the colors? Like, I'm big into colors, and you had a... Yeah.
This map, people like to look at it. I like to look at it. The colors work. But I had a slightly different vision in mind that didn't survive the production and editing process. And I was hoping to have a map where had saturated and dark gray and colors with grays and browns, like these colors here in the western and eastern melange belts, or the colors of the Methow, or for that matter, the colors of the Swak. Darker colors for the superficial rocks, the rocks that were high in the late Cretaceous and since, surrounding a light-colored glowing core of the crystalline core of the range that as recently as 45 million years ago was still warm and has been coming up out of the earth. So a sense of sort of peeling back the covers and seeing the warm glowing stuff underneath.
That would have been cool, man. That would have been cool.
Now we've lost the spatial referencing of the rocks. They were sitting on where they came from.
You're kidding me. Seriously?
Seriously.
Okay, well, let's do it. What? Can you put them back? What was the plan here? God, I already screwed it up.
This is the Sulfur Mountain Pluton, just north of Glacier Peak, which is remarkable for the great big green clinopyroxenes that are conspicuous enough that they're good for 101 lab quizzes.
Yeah.
And it's a late Cretaceous Pluton. I don't know if the Sulfur Mountain's been dated directly, but it's probably 90 million years old-ish.
Can I slow you down? I don't know where that is specifically.
Well, here's Glacier Peak.
Okay.
Here's Darrington.
Yes.
So we go down the Sauk and up the Swaddle,
Okay.
to the north side of Glacier Peak.
Got it.
And Sulfur Mountain sits just west. Oh, come on, I can't find things. Image Lake is over in here. Many people have been to Miners Ridge, the Image Lake Lookout. And it's a famous picture spot for Glacier Peak and views to the south.
Okay.
And Sulfur Mountain sits to the west of there, just west of the south end of the Ptarmigan Traverse.
Okay. And you grabbed that because the sample was handy, but is it also a key unit for you and just generally?
Nick, you said you wanted to talk about the Ross Lake Fault Zone and the Passaten Fault and about Baja, BC.
Absolutely.
And the question of, can we trace these rocks to these rocks? How much displacement is there on the Passaten Fault? And this is jumping ahead.
You're prepared. Come on now, you're prepared.
This is the next rock sample. This is a piece of the 10 Peak Pluton, which is here southeast of Glacier Peak. And at a first glance looks also very much like the Mount Stewart batholith. And it's a tonalite, a biotite hornblende tonalite.
Okay.
Similar rocks are found in the Black Peak batholith, in the the El Dorado orthoneiss,
Okay.
which here is colored light because it was metamorphosed in the early tertiary.
Okay.
In the Passaten stock, in the Fawn Peak stock. Throughout this area, there are 90 million year old tonalites or granodiorites. And you cross the Passaten Fault and we don't find any.
I've been trying to learn new things about the Wenatchee block, so folks can recognize the Straight Creek Fault. They can recognize the Eniat Fault. So, and here's Mount Stewart with the hook we were talking about in the stem and the mushroom of the Mount Stewart Pluton. And then if you've been following along this summer, so most recently I have been dealing with the Chelan block and trying my best to learn about the Swakane. And here's the Eniat Pluton, and then the most recent video, which was shot just a few days ago in the smoke, the Chelan Migmatite. And I finished up wondering about, like, I got to go talk to Ralph. I'm lost as soon as I cross the Ross Lake Fault Zone. So there's the orientation to help tie into what we have been doing.
Yeah, and similar rocks are found in the Chelan block and in the Methow block,
Okay.
but not in the Okanagan block as far as I know. The Okanagan block is not that well known, but the Plutons appear to mostly be 10, 20 million years older. This is hard to see. We're looking at the Canadian border here, and here's the Arc of the Columbia. We're in Wenatchee down here, bottom of Lake Chelan. So the North Cascades are here.
Got it. Thank
This is
you.
the Okanagan Valley.
Yeah.
And this map has, I went to the Washington State Geological Survey Geochron database
Okay.
and said, give me all the hornblende argon ages, which are the purple spots, that are between 84 and 97 million years. And give me all the zircon uranium lead ages, the yellow spots that are in the same age range.
Hey, nice.
And there are a whole bunch of them in the North Cascades and a very few in the Okanagan Highlands, and only one zircon that's east of the Okanagan River Valley. This line is roughly where the Passaten Fault is. And the pink are rocks that are Cretaceous tonalite or Cretaceous granodiorite, and that's out of the state 100,000 compilation. And it doesn't have the age discrimination to discard the young late Cretaceous or the old early Cretaceous. And I think that's why we have all this in here. This is early Cretaceous Okanagan Range batholith.
Well, just being a simple-minded person, I assumed everything was coming out of a Pluton. All these dates are coming from a Pluton, but they're not?
Most of them are from Plutons.
Okay.
Not all, but most. And some of the Plutons don't show here because they're metamorphosed Plutons and are not coded as Cretaceous granodiorite or tonalite
Okay.
in the database. And this was, 5 minutes before my morning coffee.
So one more time, viewers. Wenatchee block crosses Strike Slip Fault, the Eniat Fault. Chelan block crosses Strike Slip Fault. That's the Ross Lake Fault Zone. Another block, the Methow block in Do you like these colors, by the way? Okay. And then cross the Passaten Fault and into the Okanagan block. And I guess if we continue, there's a block over here, NW.
Northwest Cascades System.
Northwest Cascades System.
I know not very much about the Okanagan block.
Okay.
And not very much about the rocks to the southwest of the Darrington Devil's Mountain Fault Zone. And I know much less than I would like to about the southern Wenatchee block.
Okay.
But I've worked in the Wenatchee block and have seen many of the rocks.
Sure.
And I say in the southern southeastern Chelan block also, I mean, how the Skagit gneiss turns into or doesn't turn into the Chelan migmatites, I don't know.
Well, now we're down to about 2.5 people that really seem to really be thinking carefully about that, as far as I can tell.
We can invite Chris to talk about it.
Yes, yeah. Right.
So this is the geology I didn't do in the late 1990s.
Well, I've just been having a great time with this.
Yeah, that volume had a very long history. Yeah,
this volume here.
And publication, yeah.
So viewers, you remember this is how I ended the last video, where I cracked this thing open and I realized that Roland and Ralph are laying out beautifully. I'm most interested, I haven't even read this earlier part yet, but it was just perfectly timed for me to get to your, here. I think you have 6 enigmas. And that's what I'm hoping we can discuss in addition to what you wrote. But the first message is you didn't write this in 2016. You wrote this in 2000.
As we're finishing this map. So
I see.
2004, 2006.
So it's been 20 years since you've even thought about writing. You don't even know what you wrote, maybe. I don't know.
No.
Well,
you're going to remind me. So
okay. Yes, I am.
I did my dissertation on the Ross Lake zone up here, just north of the border in Canada and BC.
Oh, wow. Really?
And there the Ross Lake zone is a couple of kilometers in which you go from upper amphibolite facies Skagit migmatites to essentially unmetamorphosed Hosamine group. And there are intermediate amounts of metamorphism in between. You can step down in grade progressively across there. It's not a simple sharp break, but there are discrete changes in rock type. You go from migmatite to schist to less metamorphosed schist to greenstones that are very little metamorphosed. And this is a rock from this in the Skagit gneiss right next to the Ross Lake Fault. And it's got a beautiful fabric, no orientation at all there.
Thank
and
you.
Yet if you look at any of the sides,
oh yeah,
strong fabric and strong fabric. This rock is an L-tectonite. It's knitting needles all lined up like this. And to me, it says it's been stretched this way. And I should put the rock in spatial orientation. It was stretched along the Ross Lake zone, or in that northwest, southeast horizontal direction. And this rock appears to be an offshoot of a Pluton that Peter van der Heyden dated as, and I don't remember the exact numbers, 42 or 44 million years old.
Oh.
So this is late Middle Eocene, or post-late Middle Eocene ductal deformation in the Skagit gneiss. I also worked out what the Hosamine was as best I could. I mean, those are the two things I dealt with.
I see.
I collected Hosamine, and how old is it? What's the basalt geochemistry? What do the rocks look like in the field?
Once we get into the blues and the greens, we're in the Methow block. How much of that is Hosamine, and is Hosamine an oceanic story?
The Hosamine is the dark bluish gray in here, stretching from the Ross Lake Fault to the Jack Mountain Thrust.
Okay.
And yes, it's an oceanic story. The Hosamine is probably latest Paleozoic seafloor with a late Triassic seamount built on top of it. And the distinctive rocks of the Hosamine are either basalts and gabbros of the ocean floor and the superimposed seamount, and then especially wonderfully chaotic deposits that I thought of as slump facies that are basically things that avalanched down the sides of the seamount.
Huh.
And when I worked there, it was only a few years after people had discovered that the Hawaiian Islands are fringed with big aprons of submarine landslide debris. And I thought of that and said, that's what I'm seeing, because, and the biggest one was finding basalts that had no bubbles in them, apheric, or they were massive, and basalts were full of vesicles. So shallow water, they could degas, and deep water, too much pressure, the gases couldn't exalt, mixed together. Carbonates that look like they're shallow water carbonates mixed in with cherts that probably are deeper water deposits, and all quite chaotic, mixed on many scales. And maybe I should say part of then that helped me think about that, as I'm a backcountry skier and think a lot about avalanche hazard, and have been reading my book about avalanches and knew from both the book and experience that the wide variety of textures you find in avalanches, from powder snow, it's all fluff and settles and you don't know it's moved, to the spring wet snow avalanche that's got big globs of this and that and the other. And then as a kid, I grew up in McGilligan's Pool from Dr. Seuss. And on one of the pages, we consider the possibility of finding a fish that slides down the sides of strange mountains on skis. And it showed, and the picture was of a tropical island, steep-sided, and a fish skiing down the slopes.
I
so
remember,
a seamount. And of course, they'll be ringed with, it's a snowfield ringed with avalanche deposits, and connect the dots. Oh, the Hosamine is slump facies. It's submarine avalanche deposits, but they're rock avalanches, not snow avalanches.
Pretty cool.
And a lot of the Hosamine is late Triassic, from the chert ages, and the clinopyroxenes and the basalts have a purplish tinge to them, indicating a high titanium content that's typical of seamount basalts.
We're still talking just on both sides of the Ross Lake itself.
Yeah, this is the Hosamine in here. And then the Ross Lake Fault proper is the line you can map north of the border and south of the border that separates the Hosamine from the Skagit gneiss. And when you get across the south end of Ross Lake, the story gets a lot more complicated. And I can't tell you a simple story that tells how the unmetamorphosed rocks of the Meta relate to the highly metamorphosed rocks of the Skagit gneiss. There are lots of in-between rocks, and this is one of them. And this is a chert pebble conglomerate that's been metamorphosed and stretched, just like that granite. Again, look at the end, and you can see the pebbles, and they're roughly round.
Beautiful.
Look at the sides.
Wow. They're
all stretched out. And this rock comes from Easy Ridge over in here, where it's in metamorphosed rocks that are of middle grade, but is probably a piece of the Virginian Ridge Formation out of the Methow.
There in the middle of the Chelan block.
Well, on the inside the east edge of the Chelan block.
Okay.
And if you look at the map, if you go to the south of the Twist River, you can again map a fairly sharp line that separates little metamorphosed rocks of the Methow from, in this case, orthogneisses of the Chelan block. And we go up the Twist River and things get complicated. And that fault looks like it becomes a fault that's inside the Methow. There may be other faults in here on the valley bottom we didn't map. There's some sort of complicated progression. There's a high strain zone here along the Rainbow Lake schist on the west side of the Oval Peak. It's messy. But there's still clearly a break from unmetamorphosed rocks to metamorphosed rocks. That's well defined in here.
And mismatched.
Yeah, and if you keep going south now, south of the Cooper Mountain batholith, and you get out into the country that's north of Chelan, west of Pateros, Bob Miller had a student, Frank Raviola, who did a master's thesis in there in the 80s, and he couldn't find a Ross Lake fault, as I recall. And Roland and I spent a couple of days driving logging roads down here, and it's very frustrating. There's essentially no outcrop. The country rock is granitic and has come apart, and you get hill slopes covered with granitic grus. You can't see anything in place. When you find a rock you can hit with your hammer, it's a piece of dike. and you're up high enough that it's, and far enough south, it's not been much glaciated, and there's basically not much outcrop. And so this is basically terra incognita. Don't know what's down there.
It could be, that fault could be there,
Could
but
be
it's
there,
just
or it could not be
masked.
there.
And yeah,
And
Okay.
it needs someone to go spend a lot more time.
yeah. This is working beautifully. I did that video with the Chelan migmatite a couple days ago, and Frank emailed me immediately and said, hey, you know, we were looking for that Ross Lake fault zone,
Yeah.
couldn't find it. And I was asking about a potential kind of beautiful connection between the Chelan migmatite complex and the Okanagan Range batholith, blah, blah, blah. So it's kind of funny that you brought him
Yeah.
up. You didn't come up with the Ross Lake fault zone. Who was it? Mish that kind of first recognized
Yeah.
that a fault had to be there?
Yeah, Peter was the first person to name a Ross Lake fault zone.
Okay.
But the contrast in metamorphic grade, you know, from the west side of Ross Lake
Oh,
to
yeah.
the east side is pretty large.
Yeah.
And also then the change from Hosamine, which just looks old
Okay.
and is ugly and dark green,
Yeah.
going across this fault into the Methow, into sediments that are very little metamorphosed, and you look at it and say, that's a sandstone, that's a mudstone. That's pretty obvious, and I think Peter recognized that right away.
Is that the Little Jack fault?
The Little Jack is in here,
Okay.
and Little Jack is this light green unit,
I see.
and
But is there a Little Jack thrust as well?
this is the Jack Mountain thrust.
Oh, Jack Mountain thrust. Got
Yeah.
it. Yes. Thank
And,
you. Yeah.
I suspect it is a thrust. We were able to draw a map pattern where it goes east on the ridges and west on the valleys, east on the ridge, you know, so V's, indicating that it's dipping to the west. And as Peter understood, the geology makes sense in terms of a big thrust complex on the west edge of the Methow. The Methow has an assortment of older deposits. There are Jurassic arc rocks of the Ladner and the Dewdney Creek formations that aren't exposed much in the U.S. There are similar rocks in the Newbie to the south that are, we've colored these various blues. They're Jurassic and also Lower Cretaceous volcanic rocks. There are, look at the colors here, bits and pieces, shallow marine and terrestrial rocks that you find in the lower Chewok Valley.
Here's Mazama, by the way,
Yeah.
if folks are having a hard time placing themselves.
And this is Winthrop
the
down
town
here.
of Winthrop is there. Thank you.
And so these in here, there are, say, shallow water rocks that get as young as early Albion, and that's the Patterson Lake unit. And they're distinctive. Either they've got fern fossils and pieces of wood in them, so they're terrestrial, or in the case of the Patterson Lake, they've got stout-shelled clams that lived in a high-energy environment, so a surf zone, that say they're shallow water. And you can find those on the east side of the basin. You find them around Patterson Lake here. You find them also up at Dead Lake, which is someplace, it's north, up in here.
Albion age means like 110 million?
Yeah,
or something?
110, 105.
Okay.
And those are, at least locally at Dead Lake, overlain by deep marine sandstones in the Harts Pass Formation, and which are these beautiful turbidites, you know, big packages, you know, sands this thick, then they fine upwards and have a thin mud cap on top, and then the next sand. And if the next sand erodes the mud out, then the sands are amalgamated and they're even thicker. Very substantial rock. It's a ridge former. It's also geologically stiff, and this big thick package of Harts Pass is what makes the folds in the Methow so big, because we're folding a very large, thick thing, and it folds into big folds. And then the basin fills in, and we see fluvial deposits on top of the Harts Pass. The Harts Pass is east-derived, and we need a basin deepening event. And then the rocks on top are both east and west-derived. The east-derived rocks, both the Harts Pass and the younger Winthrop, are coming off a granitic terrain, which is probably something like the Okanagan Highlands, the Okanagan Block. The We don't have a lot of west-derived rocks of Hart's Pass age. There's some candidates, but anything I tell you about them is mostly fantasy. But we get up to Winthrop, there's an equivalent interfingering west-derived unit that's the Virginian Ridge Formation, which is full of chert pebbles, which is the kind of thing you would get if you eroded the Hosamine, because the greenstones, the metabasalts, turn into clay and wash away, whereas the chert makes chert pebbles and chert sand. And the Virginian Ridge is mudstone and mostly chert pebble and chert sand rocks.
So these are truly sedimentary units today? They haven't been metamorphosed much, if at all?
Not much. There's a little bit of incipient biotite in many of the rocks in the western Methow, probably related to these small plutons that are intruding into it. But no, they've not been much metamorphosed, and I would guess they've not been deeper than 10 kilometers or so.
Okay, well, yeah, please.
Anyway, so you have a story here of something happens in the mid-Cretaceous, actually in the mid-Albian, about 105 million years ago, that the Methow, the bottom drops out.
Huh.
We fill it with sand coming from the east, and we fill in the basin, and then we see a western sediment source that's chert-rich. And to me, that looks like we've got a structural platform or a plate margin, perhaps, maybe not a plate margin. We put a thrust load on top of the west edge of it, and we depress it with the thrust load. And then the thrust load comes closer, the basin fills in, and we start eroding the thrust sheet as it becomes emergent. And so I think both in the deepening in the mid-Albian at the base of the Hart's Pass and at the onset of chert pebble sedimentation from the west in the Virginian Ridge in the early late Cretaceous in the Cenomanian and Turonian, that we're seeing the Hosamine thrust sheet first showing up on the scene and then emerging and eroding and making debris.
Are those thrust sheets active starting about 100 million years ago?
Well, the implication is starting at about 105.
Okay.
So it's the beginning of Hart's Pass sedimentation.
Yeah.
I read the Hart's Pass as recording the initiation of thrusting. And then thrusting continues, the basin fills in, and then thrusting advances enough, the thrust sheet goes above the waves and starts eroding, and we see west-derived debris coming into the basin. And that's happening at 95-ish, or 98, somewhere in there.
Are you sure you haven't been thinking about this stuff for 20 years? I mean, this all is like, it's all fresh.
Okay, I cheated.
I'm so impressed.
Roland hired me to work with him on this mapping project, which is 800,000 sheets, 830 by 60 minute quadrangles. And when I was hired, he had done the Wenatchee, Chelan, Snoqualmie Pass, Skykomish River, Sauk River, and I worked with him on the Mount Baker. And then we began on the Robinson Mountain, and then the project was terminated by the reorganization of the Geologic Division.
Yeah, we're still 25 years ago.
We put together this map. This is the only place the Methow geology we did has been published. And I still have a more detailed map with a couple thousand strikes and dips on it sitting on my hard drive in my office upstairs.
You do?
And I've been thinking about that, finishing that as a retirement project. And so, yes, I have been thinking about this more recently.
I guess I'm surprised that we're so out of the crystalline core so quickly. We're out of the hard rock, we're out of the metamorphic rock.
That rapid leaving of the crystalline core, that's the Ross Lake Fault Zone.
Ah, yes.
That's what it is. It's the transition from one kind of geology to another. From rocks that are migmatites, schists, deep plutons and metamorphosed, to sandstone, mudstone, fossils.
In much the same way as you're driving Highway 20 from Cedro Woolley and you cross the Straight Creek and you're surprised that you're suddenly into it.
Which is why then Straight Creek Fault to the Ross Lake Zone, in between is the crystalline core. And to the west are low-grade rocks, which happen to be in part old metamorphic rocks of the eastern. And to the east are unmetamorphosed rocks of the Methow.
Wow.
And it's easy to understand how Peter was tempted to and mostly succeeded in fitting this geology into an alpine model.
What do you mean there?
Where we have a convergent origin that sends thrust sheets out in both directions, and in the middle we exhume a metamorphosed core. And the part that didn't work very well is he thought there was an older metamorphic basement that was remobilized. And he went looking for that in the yellow aster, and I think misinterpreted it as trying to fit it into an alpine model.
Hmm. So how do you see it differently?
The yellow
not
aster is not a continuous basement complex. It wasn't a layer underneath everything.
I see, I see, I see.
It's one more set of chunks inside the Belpass melange.
Yeah, yeah. Okay, well, God, this is so excellent. Before we leave this kind of non-crystalline core story just so abruptly, was it McGroder or others that were trying to make some connections between these two non-crystalline core areas and run some thrust faults through and that sort of thing?
Mike did a masterful job of taking 40 more years of work and putting it into Peter's story of thrusting going in both directions out of the core of the range.
Oh.
I mean, Peter saw that there was East Virgin thrust, the Jack Mountain, West Virgin thrust, the Shuckson, and thought they were all mid-Cretaceous. Mike, and then we did a whole lot of geology. And Mike did a very, very nice job of showing how you could explain all that geology in terms of Peter's story of East and West Virgin thrusting.
But it was one of your enigmas that McGroder's correlations you felt weren't, they were attractive, I forget the phrasing, they were attractive but still not totally in sync with what we know?
There is a whole lot of fabric in the range, and this rock and this rock are part of it, that argue for transport to the northwest, or from the northwest, along a northwest-southeast axis. And Peter's story and Mike McGroder's story was of shortening in this direction.
I see.
And it may be this shortening happens while we're also seeing transport. Maybe it's one then the other. But the question is this a convergent origin or a strike-slip origin or some combination of the two?
Yeah.
Is an open question. And I would invite, I almost printed it up, but invite people to go look at the geologic map of California or map of North America of Central California. And if you drive through California, what's striking are the big folds in the coast ranges. And for that matter, in Southern California, there are actively growing anticlines with thrust faults underneath them that we see from both oil drilling and from the active seismology, the Coalinga, the Kettleman Hills. What's most obvious is a compressional, contractional origin. Things are shortening, where the Great Valley sequence is being folded and thrust. And it's only when you look harder you see, oh yeah, there's the San Andreas Fault on the west end of all of that. And in geologic sense, I think of strike-slip faulting as essentially being free. It doesn't have to do any structural work except for in the fault zone. Whereas contraction, you've got to fold and fault step over a large area.
Oh, wow.
And I think it's possible. I mean, what's obvious in here are the big folds and thrust faults. But it's possible they're coeval with strike-slip faults that are harder to see.
Well, that leads us beautifully to the Passaten, which is kind of where we're headed, I think. And your knowledge, you're maybe being modest, but your knowledge drops off once we get to the details of the Okanagan block. But you have some thoughts about the Passaten Fault, which is the boundary between the Methow and the Okanagan.
East of the Passaten Fault, we don't see any Methow rocks. So there's a thick Cretaceous package that's truncated at the Passaten Fault. We can map a boundary that's not perfectly straight, in parts is quite straight from here to here.
Can we get our bearings from me, maybe? Is there a town nearby or anything?
This is Winthrop.
Okay.
Mazama.
Yeah.
Twisp.
Thank you.
The Passaten Fault runs from north of Twisp, east of Winthrop, to the northwest.
Got it.
And up 8 Mile Creek.
Huh.
And into the Passaten Wilderness. And this patch of orange are the Island Mountain volcanics that are Eocene. And they are clearly faulted against the Okanagan batholith here. The rocks to Okanagan batholith. So in here we have faulting that is in part Eocene or post-Eocene. Here the faulting is post-early late Cretaceous. And we get down to east of Winthrop, north of Twisp.
Thank you.
And things get complicated. And the yellow in here, the KPC, is the Pipestone Canyon Formation. which is many things, but mostly it's coarse-grained, mostly it's terrestrial, and mostly it's got clasts that look like they were eroded off of the Okanagan batholith.
Really?
And there are pollen fossils from there that indicate that it's of early Maastrichtian age in part, so latest Cretaceous, 70 million years old. So and it's faulted against the Okanagan Range batholith right in here. It's also deposited on the Okanagan Range batholith down in here. The point I wanted to get to is we have both the Ross Lake Fault that comes down here and we lose it, and the Passaten Fault that comes down here and then we don't know what happens.
Yep.
And you'll note that both of those coincide with the east edge of our mapping. And the challenge here is we have simply not done the careful work to the east to know what could be going on. We need people to go look at a lot of rocks, take a lot of notes, collect samples, get ages, and think about stuff. We haven't done that work. But I don't know the Chelan complex well.
Right.
My impression of it is mostly from the big road cuts below Chelan of the Columbia, which are fairly mafic. And the Doe Mountain it's a leucotronjamite. It's a very light colored rock with a lot of quartz in it.
What is a tronjamite?
Tronjamite is a tonalite with unusually sodic plagioclase.
Okay.
So it's a rock found near Trondheim, Norway. And
so it looks similar to a granitic body, but it's got a little special kind of feldspar.
it's a flavor of granite.
Yeah, okay.
Yeah,
Okay.
it's unusual in that it has almost no potassium feldspar or none, and where you might expect to find andesine, instead you get oligoclase or even albite.
Okay. Seems like their work in the last decade has pointed to the fact that there's a continuous bedrock story
Yeah.
that straddles this area that should have two major faults running through it.
Mm-hmm. Mm-hmm.
And that was kind of the thought 30 years ago, it sounds like, as well.
Mm-hmm. Yeah. And the question and the hard part is, how do you work in especially a not well exposed area like this, and look at the rocks and ask questions of the rocks where both these are the same rocks or these aren't the same rocks are possible answers. I mean, it's pretty easy to go out and say these rocks are different because all rocks are different from each other. It's also pretty easy to say these rocks are the same because within, fuzzy enough glasses, everything looks the same. The question is, what things do you look for? What observations can you make? What analyses can you make that would allow you to test the notion that they are the same or that they're not the same?
So two of your enigmas from 2016, which is really 2006 or maybe whatever, earlier,
Yeah.
is that the Eniat Fault, maybe the Leavenworth Fault, were small potatoes as far as offset is concerned compared to the Passaten and the Ross Lake.
Mm-hmm.
Even Mish was talking about those, at least the Ross Lake Fault Zone, being a major fault. I thought he didn't like major amounts of translation and abhorred and was revolted by Merle's, those are Merle's words. So is Mish not the fixes type person that I thought he was?
You got to feel sorry for Peter. He was trained as and spent most of his life as being a person who believed in stuff moving. I mean, thrust sheets could go 100 kilometers. That's a lot of translation. That's a lot of movement. But towards the end of his life, plate tectonics in my mountain range, you can't do that. We can't have thousands of kilometers of movement.
Wow. Okay. Yeah. Interesting.
And Peter and then following Mike McGroder argued strongly and well for 100 kilometers of shortening or more this way. And in that sense, they're mobilists.
Oh, I get it.
We're looking at potentially 1,000 kilometers or more along here, or maybe it's 700 here and 100 here and 50 here, and
so you can have a mobilist fixist debate with thrust faults in a horizontal sense, and that sometimes is a completely different discussion than the same discussions along strike slip faults.
Well, yeah. Well, not only that, not just strike slip versus thrust, but also 1930 or 1940 versus 1980, 1990, pre and post plate tectonics.
Yeah.
Pre-plate tectonics in 1930, 1940, when Peter was trained, actually I should say 1940, he came to the Cascades in 1949. He was a mobilist. In that time period,
I see.
Seeing 100 kilometers of overthrusting, that made you a mobilist.
Interesting.
And then the context changed, and we discovered plate tectonics, and everybody's looking for thousands of kilometers of translation.
Is Quinella on this map?
This may be Quinella, the Okanagan block. The problem here is there's very little supracrustal material. Very few volcanic rocks or sedimentary rocks that have a stratigraphic identity that says this is anything. These are mostly plutonic rocks. But as you go along strike to the north, it looks like they're intruding Nicola.
Well, that's, to me, my most current major puzzle is that I'm working my way through the crystalline core. I'm feeling like I'm making some connections, and before I know it, I'm driving from Pateros up to Carlton or whatever, and I see Quinella on these maps or in a road guide or something. I'm like, what happened? How did I?
Yeah.
I talk about a surprise. Where's the Cache Creek? Where's Tequila? Where's all the Quinella?
There's Cache Creek. There's Cache Creek.
Hosamine, Cache Creek.
Hosamine, Napiqua.
Napiqua.
Those are Cache Creek-like rocks. The Cache Creek, the Hosamine, and the Napiqua are all originally chert, greenstone, scattered ultramafics. They're pieces of the Paleo-Pacific Ocean floor. And you could say it's one terrain, but if you think how big the Pacific Ocean is, that's not a very meaningful statement.
Yeah.
But they're a facies, a set of rocks that belong to an old Pacific Ocean, which may have formed thousands of kilometers apart, but they're similar. But the Ross Lake or the Passaten, I think I actually, for the Ross Lake, spent a page enumerating in a 1994 guidebook that I saw you over there, enumerating the different disguises the Ross Lake Fault has worn over the years.
Yes.
It's clearly many things. And the Passaten Fault, you can say the same thing for it. And this is the Passaten Fault where we know it well, north of Twisp, basically. South of Twisp, maybe it doesn't exist at all, or maybe we simply have failed to understand it for lack of work.
So that crystalline core could be, at its most basic level, a metamorphic core complex.
Oh, yeah.
And that's not a controversial thing to say? The timing is just so similar to these other metamorphic core complexes in the Northwest, right?
Yeah. I think I once gave a paper about that. An abstract got published, and that was all. But yeah, the Skagit Gneiss, or the crystalline core, the northern Chelan block, is in many ways a core complex. It differs from the classic core complexes farther east, the Shuswap, or the younger core complexes of the northeastern basin and range, in that the associated faulting appears to be in large part transverse and not simply extensional. So the Skagit's probably a transtensional core complex, not an extensional core complex.
Okay.
There are a lot of very ugly rocks along the banks of the Columbia between here and Chelan that make me think I'm driving around the Whipple Mountains in Southern California.
Which mountains?
Whipples?
The Whipples.
Daryl sent me on a field trip once where we walked through the Whipple detachment and saw a lot of really beat up rocks. And I think of that often when I stop on Highway 87.
Last thing. In your first interview with me, I don't know, I'm guessing you didn't come up with it on the spot. You said I toyed with the idea of doing some sort of incredible Cordilleran thing from Nicaragua to Nome.
Mm-hmm.
And that stuck. Of course, people still remember that. So here's Robert Hildebrand. I don't know how much you've dealt with Bob, but he's trying to do something similar, I guess, to what you were thinking you might try to do. Mm-hmm. Or is this what you had in mind?
This is the extent that I had in mind. And I actually don't know this map. Do you mind if I unfold it?
Please.
Look at the legend.
I'm happy to leave this one with you. So I'm springing it on you in real time here, but he's a synthesizer.
Yeah. this is the kind of map is similar. I wanted to make a map that would be about 3 times bigger in linear dimensions, so 9 times bigger in area. So more detail.
Okay.
And I think the question here is not what happened in the late Cretaceous and the early Tertiary. So these rock units are, if you will, are cover.
Mm-hmm.
The question is the early Jurassic, the Triassic, the Slide Mountain, the McLeod and Tethyan, these stratigraphies to document them in more detail and see where they fit and where they don't fit along strike. You know, can I find this stuff, the Slide Mountain, and he's got it here and here, you know, how far along the Cordillera do we trace it?
Mm-hmm.
And it would be nice to be able to show that this geology matches this geology or doesn't match it. And it doesn't immediately strike me that he's tried to do that on this map, to make a map that tests whether we can fit, whether this geology fits better here or here or here when we restore the faults.
Mm-hmm.
That's what I had in mind. Not saying this isn't an interesting map.
Well, he's similar to you in the sense that he's zooming out, of course, from here. And
Mm-hmm.
as you were saying in the interview 2 years ago, you're like, if you're working with faults and the offset is larger than the scale of the map, then
You're lost.
You're lost.
Yeah, and so you need a map this big to, as a mapper, approach the Baja BC question. This is the map extent you need.
And if you're unaware, Bob has written a paper 5 years ago saying all the Baja BC people are not looking in the right place.
Mm-hmm.
They need to look on a scale where we're offsetting much further inland.
Yeah, and we now are doing, there are any number of papers that are looking at comparisons from the northwest to the near the U.S.-Mexico border.
There are?
Southernmost California.
Like Kirsten Sauer?
Yeah.
Okay.
Yeah.
Yeah.
And that's one of the implications of saying that the Swakane looks like the Rand Orocopia Polona schist.
Mm-hmm.
Is either there was a belt that went the length of the Cordillera or the length of this part of the Cordillera, or we've translated from there to here.
Mm.